Alright, so we're going to start Chapter 14. This is all about what is stellar evolution. As stars are born, they age, and then they die. So we actually have an entire chapter on the death of stars. Alright, we'll get into that a little bit later. Alright, so the life of a star. The main thing is, it's really gravity that holds the star together. And so, if gravity was the only force present, then the star would just collapse. All stars would just collapse. There must be something pushing against gravity, against the pull of gravity, and so that push is really the conversion of hydrogen into helium. There's a pressure, an outward pressure that is caused by converting hydrogen into helium. It's an explosion, right? It's a nuclear explosion. All right, so that's that's the thing that I want you to realize is most of the time during the life of a star, there is this balance between gravity, the inward pull of gravity, and the outward pressure due to fusion, right? The conversion of hydrogen into helium. Right, and now that doesn't last forever, as it says down here, right? Towards the end of a star's life, they die, and basically what happens is eventually gravity wins, right? The fuel supply runs out, and we're going to talk about that. All right, so actually that's what this part is about. Towards the end of, well, here, let me go through this. All right, so you have this balance between the inward force of gravity and the outward pressure due to fusion, and for a very long time, in some cases like our star, billions upon billions of years will go by. For our star, we think it's anywhere from 8 to about 10 billion years, where it'll just keep, in a nice stable equilibrium. But then, when the hydrogen fuel supply runs out, basically what happens is the star collapses, and then if eventually the star contracts so much, and the internal heat gets so high that the next element, helium, which is going to be inside of the core, begins to fuse as well, and so forth down along the periodic table. If a star is massive enough, then what happens is the star can fuse all the way up to iron. And iron, if you look on the periodic table, is element 26. And so really you might ask, how are the other elements created? And that's a really good question. That happens for really massive stars during the final instant of their life. And during that time, when the star is becoming, so that's this direction here, going, a very, very massive star becomes either a neutron star or a black hole, and during the final instant of its life, they explode, and they create the rest of the periodic table, the elements of from iron all the way to uranium. All right, and so, but what about the vast majority of stars that are not as massive? Many times the mass of the sun, or even less, which is the majority of stars. They're less than the mass of the sun. Those stars become what's called a white dwarf, and so we're going to go into what exactly that is. All right, so really the key to the amount of time that a star is going to be around is the the mass, right? It really is as simple as that, right? The mass will determine how long a star is around. So now it's actually kind of opposite what you might think, right? Let's see, is this the next? It's actually opposite what you might think. So really massive stars, they do have more fuel supply, but the problem is they go through that fuel supply a lot faster. Whereas like a tiny star, like really, really small, like let's say 1/10 the mass of the sun, that those stars will be around for many, many, like billions of years longer than the sun. So let's say the sun's our star will be around for 10 billion years, roughly, anywhere from 8 to 10 billion years. Some of these much less massive stars, like let's say a tenth the mass of the sun, will be around for many times that, right? Many billions of years. All right. In fact, we know that the universe is 14.8 billion years old, and so there are stars that where there hasn't even been enough time in the age of the universe for those stars to die. These small, like stars about a tenth the mass of the sun. All right, so yeah, I mean, remember, gravity is the thing that drives the evolution of the star. That's the important thing. All right, so let's go through the birth of a star. Comes from these giant gas clouds. They have various shapes, but once gravity takes over, and of course gravity is always there. What I mean by that is gravity takes over so that most of the particles in this gigantic cloud. I mean, these clouds can be many light years across. Tens of light years across, sometimes even hundreds of light years across. At any rate, they are, gravity causes these things all these particles to accumulate into towards a single point, and really, at that point, the physics, we understand the physics quite well. These things will begin the particles will begin to rotate and flatten out. And that they become what's called a protostar. That's not a star yet. It's just something that's getting hot because gravity is, bringing material together, and when material gets close together, it rubs together and it gets hot. And then eventually the star is born. And actually, before it's born, these protostars, some of the material will leave, as you can see there along these bipolar flows. These have to do with the magnetic field of the star for the direction. Anyhow, then the star becomes a sun, a full-fledged star. It gets up onto the main sequence, and then it'll last. It depends on how much mass it has. Remember, the smaller the smaller the mass, the longer it's going to be on the main sequence. So those really massive stars, those O stars, don't last, but maybe 100 million years or less even sometimes. So a star. Well, this is a star like our sun. Okay, so a star like our sun, it would become what's called a red giant. Massive stars do this as well. So they expand. Now you might wonder, well, why the heck are these things expanding? What happens is gravity, of course, squeezes the star before it expands, and then it will fuse helium. And when it's fusing helium or even heavier elements, it puffs out. It pushes that new fusion process pushes the outer layers of the star outward. All right. So it goes through the red giant stage. As it fuses new elements, it shrinks and then it expands again. It shrinks and expands. Those are what we would call the variable stars, the pulsing stars, or variable stars. Actually, pulsing is not a good name for that because there's another type of star called a pulsar, which is a dead star. We'll talk about that later. All right. So one of the things that happens to ordinary stars like our sun, so there's one solar mass or less. Actually, can be a little bit more massive than the sun too. At any rate, these stars will eventually they lose grip on the outer part of of the mass, and that outer part drifts off. Reaching escape velocity, it drifts off out into the universe, and that is called a planetary nebula. So that's the planetary nebula. So after the red giant phase, there's this planetary nebula phase, and then what's left is a tiny, tiny core, like roughly the size of the Earth, or even smaller, a little bit smaller sometimes. Which is mostly, it turns out that it's mostly carbon. So this is like an extremely dense, like kind of like an ember. It'll glow. We can actually detect these from their light. These are extremely hot, but they're very, very small. These are what we call white dwarfs. All right, so again, that's after long. This planetary nebula stage doesn't last for maybe 100 billion years, or 100 million years. Sorry, or less. And this white dwarf stage can last for. We have no idea actually. We think that these things will be around for hundreds of billions of years. All right, planetary nebula stage, then white dwarf stage. All right, this one's short. This one is much longer, and of course the red giant stage doesn't last all that long either. It's like in the millions of years. So for a high mass star, it's the same starting point, but you're accumulating more mass, and the same thing happens. So you eventually. The protostar eventually becomes a star, and then the star goes through its life cycle. Its life cycle doesn't take as long, right? It's got a lot more hydrogen to burn, but now, by the way, when I say burn, I'm talking about nuclear. It's not a chemical process at all. It's nuclear, but often astronomers will refer to it as burning. At any rate. So the star burns through its hydrogen fuel supply, and then of course becomes a pulsar. A variable star, and it goes through the red giant stage. But see, the thing is, when the star begins to fuse, the moment it reaches iron in the core, right, where and it tries to fuse iron, it can't, right. It's the reason is it has to do with nuclear physics, but it can't. And then there's the giant explosion, which is one of the brightest things there is in the universe, called a supernova. And then after the supernova stage, the star will settle down into either what's called a neutron star or a black hole. And there are conditions for a star to become a neutron star or a black hole. All right, I'll pick this up again in the next video.